Hello everyone! Today we are going to prove the second set equality, starting by proving an important theorem, the Archimedean property of R. Let's first examine the theorem. It states that, given any elements x and y from the set of real numbers R with x greater than 0, there exists a positive integer n such that n times x is greater than y. Let's prove this by contradiction. First, we construct the set A consisting of all elements of the form n times x, where n is a positive integer. Now, assume the opposite of the Archimedean property, that n times x is less or equal to y for all positive integers n. By the definition of the set A, this implies that y is an upper bound of A. Therefore, by the least upper bound property of R, the set A has the least upper bound. Let alpha be this least upper bound, or the supremum of A. You may ask, what is this least upper bound property of R anyway? Let me explain it with a fewer definitions. First, the definition of order. Given a set B, an order on B is a relation denoted by this inequality sign, satisfying two properties. 1. If x and y are in B, then exactly one of the following holds. X is less than y, x equals to y, or x is greater than y. 2. The transitivity property. If x, y, and z are in B, and x is less than y, and y is less than z, then x is less than z. Next, an ordered set is a set B equipped with an order, as just defined. Now, the least upper bound property states that if A is a non-empty subset of B and is bounded above, then the supremum of A exists in B. Returning to our proof of the Archimedean property, since x is greater than 0, we know that alpha minus x is less than alpha, so alpha minus x cannot be an upper bound of A. Therefore, there exists a positive integer m such that m times x is greater than alpha minus x. Adding x to both sides, we get alpha is less than m plus 1 times x, contradicting the assumption that alpha is the supremum of A. Thus, n times x is greater than y must hold, meaning the set A is not bounded above, which proves the Archimedean property of R. Now, let's move on to the main topic of today's video, proving the set equality. Take a look at this equality. We will split the proof into two parts. For the first part, note that to make the right-hand side of the equality meaningful, we must first accept by default that for any positive integer n, a plus 1 over n is less than b minus 1 over n. These intervals are well-defined and do not collapse to a single point. Thus, for any n, the closed interval a plus 1 over n, b minus 1 over n is a subset of the open interval ab. Therefore, the countable union of these closed intervals is a subset of the open interval ab. Now, let's address the second part of the proof. Take any element x from the open interval ab. We have x minus a is greater than 0 and b minus x is greater than 0. By the Archimedean property of R, we can find positive integers m and t such that 1 over m is less or equal to x minus a, and 1 over t is less or equal to b minus x. You might wonder, why does this make sense, and why are these inequalities non-strict? Let me explain. Let's take a look at this theorem again. We know that x minus a is greater than 0 and b minus x is greater than 0, which already satisfy the condition of the Archimedean property of R. Now, we can simply choose y equals to 1. Then, there exist integers m and t such that the corresponding inequalities with strict inequality signs hold. These strict inequalities immediately imply that the inequalities with non-strict signs also hold. By dividing both sides of the inequalities by m and t respectively, we obtain the desired inequalities. Moving on with the rest of the proof, we see that x is an element of a closed interval for some positive integers m and t. We can now choose k to be greater than the maximum of m and t, which leads to the inclusion of x in the closed interval a plus 1 over k, b minus 1 over k, for some positive integer k. Voila! This implies that x is indeed an element of the countably infinite union of closed intervals, a plus 1 over n, b minus 1 over n. This proves that the open interval AB is a subset of this union of intervals. In conclusion, the set equality we wanted to prove is true. In this video series, we have completed the proofs of these two set equalities. Thank you. See you next time.